So if you look at the diagram here, A, B, C, D, E, F, this is just the same thing rotated by one seat to the right. Okay, so that is going to be the same. Now, there are a couple ways of solving this problem. Hopefully you have thought of one while sitting, pause, looking at the slide, just like we always do. And this is sort of themed along the overcounting thing. It's just a little bit off there. So one method of overcounting is to use the rule of product in reverse. So if you have k copies of something that you want to count, and it's convenient to count it in a different way, with a factor of k or more, and it has to be exactly k for each of those, then you can divide by k and get the result. So this is a division rule. And we can use this here. So we're going to overcount for purposes. Okay, so solution or strategy is to overcount on purpose. And the number of permutations is normal. 6 factorial ways. Permutation without replacement. But then, like, there's 6 seats, so there's how many different rotational symmetries are there? Well, you can rotate 1 notch, 2, 3, 4, and 5. So there's 6 different ways of rotating, so it's going to be overcounting by a factor of 6. So there are 6 rotational symmetries. So, therefore, 6 factorial, 6, 5 factorial. Okay, and this generalizes as well. Okay, so another question would be, what if it's n people circular table instead of 6? Well, that would give us n factorial by n. It's the same logic. It's n factorial ways just to put the n people around the table. And rotation symmetric. So that would give us n minus 1 factorial. Okay, so that's our intro example for today. This is lecture 6. This is supposed to be a lecture in lieu of Friday, January 17th. Hi, I'm here in my office. It's morning for me, and it's Thursday morning, but it might not be morning wherever you are right now, or whenever you are. So this is in lieu of my absence on Friday the 17th. And, very sorry if you were looking forward to having an in-person class. I was looking forward to having an in-person class, but this couldn't be avoided. So we're doing it this way so that we keep up and we can have that all material we need for first assignment. That comes out on Friday, the 17th as well. Anyway, so I appreciate you taking the time out of your day. It's maybe not what everybody wanted, but I do appreciate you keeping up and doing this lecture. We are going to build on the choosing and sort of combine it with a whole bunch of other techniques and ramp up the complexity of the problems. We're building on that choose stuff from last time. Okay? And don't know how far we're going to get, but whatever we don't do, we will we'll dust that off. Okay? All right, so let's let's okay, so last time we introduced this generalization, choose, okay, selecting n of r of n distinguishable objects, so this means that the things don't have an order, and again, we use this overcounting on purpose type of idea to convert angry lines into angry models. So the angry lines were permutations. So that has an order. How many ordered objects do you have compared to the unordered equivalents? Well, there are r factorial scramblings of those r things. So we divide by a factor of r factorial. Fun fact, and we can do something similar for the permutations when we go back here. This is also a division of factorials, and if you were to try to overcount on purpose for permutations, you could do it. Okay, so here's an idea, and it's just a sketch. Okay, so as an alternate, if you wanted the number of permutations, what you could do is you could just line up all n objects, right? Okay, so you could put like n boxes instead of, so you could have n boxes instead of to the n minus 1, n minus 2, n minus 3, and so on. It's dot, dot, dot. And get to n minus r, n minus r plus 1. So n minus 1, so n minus r, n minus 2. So you could do this entire thing, just take all of them and commute them. Okay. Now, of course, that's too much, right? Because you're not commuting all the objects, you're commuting r of them. Okay, but so that's overcounting. So how much do you overcount by? Well, these are the objects that we don't care about their order. So the tail of the line, n minus r things, can be scrambled up in n minus r factorial ways. Okay. So that's the number of permutations, the number of copies. It's a whole lot of number of copies, right? But this is how many extra permutations we have if we do this really extended overcounting. Right? So same idea, we can take n factorial and divide it by n minus r factorial to develop the permutations as well. So it's kind of cute, but similar to chooses. We're going to be doing a lot of stuff with the chooses, stuff that we ended off with last time. Is this example, which I didn't quite do all of. Okay, so just to refresh you on this, how many bit strings do we have that has exactly 3 ones. And there were 2 different ways you could go. You could do choose 3 or choose 5. Select the ones with zeros, much higher. As a computer sciencey thing, one might ask how many, what's the connection between binary strings and other objects, and one common object is a set. Okay, so if the size of a set is A, you ask yourself how many subsets size 3 are there? Or if you have a set of size n, and ask how many subsets of size k are there. There's n choose k. Okay, so in this case, there's 8 choose 3. Okay, different subsets. Now, how do we tie this to bit strings? Well, this is a data structure you can use to represent a subset internally in computer. Okay, so note that a binary string can represent a subset. So if you imagine A is the 8 elements, A1, A2, A3, A8, and all the way through there, okay, then you can use you have a binary string, it's like what's above, it's positive what's above. So a 1 in position 5 means that a 3 is in position. So each of these will correspond to a certain selection of those items being in. So it's 3, 5, 6. And oftentimes when you're doing anything where you need to examine all these subsets and relate all the subsets together, a lot of these have to do with dynamic programming type algorithms. You will use this many bit manipulation to do I guess you need to do binary OR and cyclic. Pretty cool. Anyway, okay, let's do some more combinatorial. Back to a fair die. So just remember how this one went. So a die is rolled 6 times in succession. And we have an ordered 6 tuple, and we're asking ourselves, the frequency of the number 6. Okay, so last time we did 6 was rolled 0 times, and I think that was about 33%. 6 was rolled exactly once, that was about 40%. That seemed pretty likely. It was a total of 73%, and there's no other outcome that's going to be as likely as those. Okay, so how likely are the other things? So, how likely is it that you get it twice, 3 times, k times? Okay, so yeah, so the other example is around, so just remember the size of the sample space is 6 to the 6. Okay, so we're going to divide by 6 to the 6 later. Well, anyway, when we did the example before with exactly 1 time, the first blank we had determined how many ways you can put the 1 6. Okay? And there are 6 ways of doing it. We're going to do something a little bit different. Just imagine where the 2 6s go on the blanks. We can do something similar with the, as we just did with the binary strings. We select 2 of the blanks, and a 6 goes in here, and a 6 goes in here. Okay? Or just like this one, this one, this one, this one. Any of the 2. And the other blanks will have 1 to 5. So 5 choices for them. Okay, so it's a 2-step process with the rule problem. First, we select the places where the 6 goes, and we do that using a choose solution. Select the 2 roles. 6. 6 choose 2 roles. And the other roles have 5 choices. Okay, so by the rule of product, spare ourselves a little bit of writing. Okay, so we get 6 to the 2, or 6 choose 2 times 5 to 4 ways. So D is 6 choose 2, which is 5 to 4, and 6 to the 6. So, and I'm just going to expand this thing longhand. Sorry, could leave this in final form, but if I ask you to calculate it, the tail of this thing gets cancelled out, right? So 6 factorial by 4 factorial, 2 factorial, 6 factorial by 4 factorial, more or less cancel each other out. Okay, so this 5 will get absorbed in here, this 6 will get cancelled by this half. That survives. So just, we don't even need a calculator. We end up with 5, 6 to the 5 times a half. And we already did this in the previous iteration. We did this in part C, is 5, 6 to the 5, which is around 40%. So this is half of that. This is around 20%. So the most likely thing is 1 6. It's slightly better than 0 6s, which is at 33%. It's less than this, which is 20%. Anyway, so for general k, you can sort of imagine this is going to be 6 choose k, and this power will go down by 1. Okay, so for general k, 6 choose k, and we'll be left with 5 to the, I guess this is 6 minus k. There's only one way, 6 choose 6 times 5 to the 0, there's only one way. This seems to work out well for all 6s come up in all 6 rolls. But this is entire, right? So this worked for every one that we've done so far, part A, part C, here. And if you tried all possible k's, you should get 100%. You should get the entire sample space. And that is sort of something that you might suspect is like a combinatorial proof. So if we added everything from all possible k from k equals 0 to 6, and this generalized thing, 6 choose k, 5 to 6 minus k, this should total the sample space, which is this, right? So that should be 6 to the 6. Okay, so this is a combinatorial proof of this identity. But this identity has a common name. Seen this before. We're going to go over it again in a little bit. But this is a specific substitution of the binomial theorem. This distribution of throws for this is known as a binomial distribution. But it follows exactly the form of this is an expansion of 1 plus 5 to the power of 6. Anyway, okay, let's button that down. This is comfy. Okay, one more topic about coefficient sections is poker hands. I'm a little shy to talk about poker hands, not because I think they will become addicted and controllable gamblers and all this sort of thing, but because not everybody grew up playing cards. I get more feedback about this every time I do examples like this. But cards are going to be part of our common lexicon. Okay? So we you definitely need to know about those objects, right? Fair coins. Okay? So fair coins have two sides, 50-50. Dice are n-sided dice. I guess a coin is like a two-sided die. And then decks of cards. Okay? So we're going to use these things for problems. In case you've never seen a deck of cards, there are 52 cards in a standard deck of playing cards. There are 4 suits, clubs, some temporary clubs, these little clover things, diamonds, hearts, and spades. And there are 13 ranks of cards in each suit. So there are 4 twos, 4 threes, 4 fours. There's 4 through 10. And then there's the jack, the queen, the king. Actually, I listed them off in increasing order from smallest to largest. This is important because the ranks, what is adjacent to the rank or what beats other cards is important to some games like poker. Anyway, in the game of poker, you are tasked with making the best 5-card hand that you can. There's a little bit more complication than that, but in terms of what hand beats what, you take the best 5-card hand that you've got and match it up against the other person's 5-card hand, and there's a ranking order. Okay? So pairs are good, 3 of kinds, and sequences of cards in a row are good. 2, 3, 4, 5, 6, that's right. And 5 cards of the same suit are also good. That's called flush. Okay? At one time, I had more examples of this, but it became too difficult to explain what the different hands were. So we're just going to do these ones, and if you're interested in doing more computations about these, are really good problems for you to get a handle on. If you're not into poker, then this might not be for you. But if you are into poker, if you know the hands, computing the probability of each hand coming up in a selection of 5 cards is within reach, and you can verify those calculations on the internet. The answers are certainly right there. Anyway, we are going to ask, basically, what's the probability of a 4 of a kind and a full house being held? These are 2 of the best hands in poker, and I'll explain how they take place. Okay, first things first, how many 5-card poker hands are possible? One thing that might not be obvious is that the order that the cards come doesn't matter. Even though we have 2 aces here, and that's a pair, that's a hand better than a hand that has no pair most of the time. The ordering of these cards doesn't matter to the fact that it has a pair. Okay? The order in which you would dealt the cards doesn't matter. In some games it does matter your order, but in this game it doesn't. So order cards is important. So this becomes a choose. Okay, so there are 52 cards, and you choose 5. So 52 choose 5 cards. And if you ask your calculator or you ask the internet what 52 choose 5 is, you certainly get an answer. If you were ever to be tasked with computing this on your own, it will always give you an integer. But typing in 52 factorial into your calculator is probably not what you want to do. Make your calculator catch fire. It's a really big number. And there's a 47 factorial similarly there. You don't want to compute these numbers. You want to cancel them. Just like a multiplication, you cancel out the factorial tails, and you end up with d's on the numerator, and d's on the denominator. And also 52, 51, 50, 48 will give you a large number. It won't make your calculator explode, but you don't want to be in a position where you lose precision. You certainly don't want to start dividing by integers and creating decimals also. The way to do this is by sort of calculating from right to left in sorts of pairs. And if you do this, you'll never be not an integer. So it will always give you an integer. Just like this. Anyway, this is around 2.6 million possible poker hands, which makes it an interesting game for humans to play. And anyway, if there's only one way to be dealt a hand, the chance of getting it would be 1 in 2.61. So it's a very, very slight probability of getting that hand type. Ask yourselves how many ways are there of getting 4 of a kind. We could do something similar to what we did in the dice throwing example. Okay? 4 of a kind means that there are 4 of the same rank, so 4 twos, or 4 tens, or 4 aces. So the sequence in which we're applying the rule of product, okay, is going to go in a sequence of stages, but we're really using hands. So we're using hands as we go. Okay, so the first step is to pick a rank. Okay, so how many ranks are there? Well, there's 13 of them. I could say in 13 ways, but really, we're doing 13 choose 1. You can choose 1 if you work it out. So say there are like, so pick a rank, there's like tens. So the first 4 cards. Okay, now that's only part of the story because there's another card. Okay, so you can't it's not just 13 different ways to form a card. There's a 5th card that doesn't pair anything, okay, and there's just one other card. How many ways are there to pick the other card? It's not 52 choose 1. It's 48 choose 1. Because we've eliminated these 4 from the deck, right? You can't duplicate them. So there are 4 cards less. Okay, so we combine these things using products of 13 times 48, and we can run that through your calculator. It's 624. This is a very small number. I mean, it looks like a large number, but it's a very small number compared to 2.61. So it's less than 10,000. So it's really not very likely to go 4 to 5. So it's a very, very good number. Full house means that you have 3 cards that match as a triplet and 2 cards that match as a pair. So there's no extra 5th card. They're all sort of busy. Okay, but that's the prototype that we're doing. So I'll give you a moment to think about how you would approach it, but it'll be something similar. So just give it a thought for a second. So hopefully you have a plan. Here's what I suggest. Okay. So first, you should pick the rank for A. Okay. So pick card for the time. But now, the suits become relevant, right? Because we're only taking 3 of the 4. Up here we took 4 of the 4. Maybe I should have added an extra step. But there's only going to be 3 of the 4 suits, okay? So pick its suits. How many ways can we do that? Well, there are 4 ways, but really it's 4 choose 3, which is like 3 of the 4 suits. And then we do the same thing for the pair. Right? Now the pair of B's, we'll have not 13 choose anyways, but 12. We can actually have these machines here. So 12 different things remaining, and then we're going to pick its suits in 6 different ways. That's 4 choose 2. 2 of the 4 suits. So we're doing it in stages, okay? So we're finding what are the A's. So pick a rank, pick the suits, and then you sort of feel the and then in the description, right? You can sort of hear the and it should be placed. Anyway, so 13 choose 1 is 13, 4 choose 3 is 4, 12 choose 1 is 12, 4 choose 2 is 6, ends up giving something we can't compute because we're 3, 7, 4, 4. So it's around a 1 in 1,000 chance of down to full house in 5 cards. So this is multiplied by 50,000. Very good. Okay, so and you can keep doing this, right? There's straights, there's flushes, there's 2 pair, 1 pair. Do this, and if you want to, I have the answers, but the answers are out. Okay, let's talk about chooses a little bit. These binomials come up all the time. See them. Just homework examples, but most famous distribution is one to one, is the binomial distribution, and they're tied to these binomial coefficients. So here are some choose manipulations for you. Okay, so the first observation is that n choose k is equal to n choose n minus k. We saw this in the binary string example where a choose 3 is selecting zero, 0, 1s. It's basically selecting stuff that we want versus stuff that's left over, which would be n choose 5 and 8, n choose n minus k. You can verify that. That was like a combinatorial proof that we did back then, but you can verify this algebraically. So this is n factorial by n minus k factorial k factorial. And that's the first one. The second one is with the factorials based on the flop on the denominator, and of course, flop multiplication is equivalent to B and C. So there's some symmetry in the binomials. Okay, so it's just symmetry. N choose 0? N choose 0 is 1. You could verify this by doing the algebra, right? N factorial by n minus 0 factorial is cancel. 0 factorial, of course, is 1 divided by 0. You can think of how many ways are there selecting 0 of n things, right? There's only one empty set. There is 1, it's not 0. N choose n? Same thing. 1 ways of selecting n, right? So, and that makes sense even by the symmetry of those two things. N choose 1. Number of ways of selecting one of the ones, that's going to be that. You can verify this using the frame too. We saw a lot of examples of this. N factorial by n minus 1 factorial, 1 factorial. 1 factorial goes away, of course. N factorial by n minus 1 factorial. They're very close, they're just off by 5. And other problems might get you to do like n choose 2, and it's like quadratic. This is the common ones for our purposes. And now, patterns. The sum. Okay, the sum of all the chooses running from I equals 0 all the way up to n. Okay, so n choose 0 plus n choose 1 plus n choose 2, all the way up to n choose n. We did one example like this. I think it was the coin tossing example. We found that 10 choose 0 plus 10 choose 1 plus 10 choose 2, the number of heads that we can get on 10 flips of the coin, ends up being 2 to the 10. And indeed, this ends up being 2 to the n. So the sum of all of the chooses where the top of the choose ends up being stable, you try all the possible things, ends up being power of 2. So maybe I'll say a little bit more about that on the next page. And the last bit here, okay, so all of those chooses sort of taken as a sequence. This is from an object that you've probably played or had with as a kid in grade school, high school. Okay, so these are precisely the numbers in the nth row. Pascal's triangle. Just to refresh your memory of Pascal's triangle, this is it over here. Okay, and you start with a C value of 1, and then you sum, you sort of go 2 different ways in each direction. So this 1 gets split into 2, and 1 plus 1 gets you 2, and 2 plus 1 gets you 3, so 1, 3, 3, 1, 1, 4, 6, 4, 1. So these are precisely the chooses. Okay, so you can see them over here. And so 0 choose 0, 1 choose 0, 1 choose 1, and so on down the table. So this is 0, 0, this is 0, 0, 1, 1, 2, 3. And you can sort of see the patterns, right? Like you can add up the rows here. You can see it. This is 1. This is 2. 1 plus 2 plus 1 is 4. This 2 plus 2 plus 1 is 8. So you can see the powers of 2. Looking at it here, it looks kind of obvious that it's always going to be a power of 2, because each of these numbers feeds into 2 things in the next row. So it's it's contributing twice, so it must double to get the next row. So double. And there are many patterns in Pascal's triangle as well. One thing that might not be obvious, but it turns out to be true, is that the even chooses, so choose 0 plus 1 choose 2, so whatever the even chooses are equals the odd chooses. Okay, so that's interesting. Now, it looks like it's pretty obvious on any of the odd number rows, right? Because they're symmetric. Right? So 1, 3, 3, 1 run the same forwards as backwards, right? So they clearly cancel each other out. But it might not be obvious for the even number rows, like 1, 2, 1. Right? 1 plus 1 happens to equal 2. 1, 4, 6, 4, 1. 1 plus 6 plus 1 is 8. 4 and 4 are 8. It turns out that it works, and you can do something similar by looking at the way that numbers are feeding down row by row. You end up adding things once together to get all the odd positions, and then once to get all the evens. You can prove this thing algebraically as well. Believe it or not, the Fibonacci numbers are here as well. To see them, remember Fibonacci numbers, like the sum of the 1 equals, sorry, the 1 equals the sum of the 2 previous, right? So 0, 1, 1, 2, 3, 5. Anyway, if you do this sort of this angle cut, so 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 plus 1 is 5. So if you keep on doing that angle, you get Fibonacci numbers. Anyway, the one that we care about here is that the sum of two chooses gives you a third choose. Okay. That is something that Pascal discovered many years ago, and algebraically, we can rewrite this as, okay, so if we have two adjacent chooses, so this would be n choose r plus n choose r plus 1, this is something that's adjacent. This will give us the choose on the next layer, which is n plus 1 for the top one, and the bottom will be r plus 1. So it's there. Okay, we want to make sure the chooses don't go off the edge of the universe, so this is for any r that's there. So that's Pascal's identity, and you can prove it by doing algebra, by expanding factorials, but you can also do it by counting. Okay, so we're going to do a combinatorial proof of Pascal's identity right now. So, okay, so just to refresh your memory about how combinatorial proof works, there are going to be two ways that we count a collection of objects, two distinct ways, and because they're the same set, counting entirely, there is a bijection mechanism, so there must be equality between those two things. Okay, so we are going to count the number of subsets of A. A is a set with n plus 1 elements. We're going to take the number of subsets of size r plus 1. So let's do it. Okay, here are two different ways. One, we could just do n plus 1 choose r plus 1. The number of subsets of A with r plus 1 elements is n plus 1 choose r plus 1. Okay. This is the right hand side. Okay, that's the easy way. The other way is to examine any specific element x. And say, okay, well, let's look at the case where x ends up being in the subset, or x is not in the subset. There are two cases, right? Okay, so let's do that. Okay, so first case will be x ends up being in the subset. Now, how many different subsets are there where x is included? Well, we need r more elements to make up the difference, right? Because there's already x's in there, so it's one of the elements, we need r more. And out of the remaining n. Okay, so we need, so then the rest of the elements are going to be r of the n remaining elements. So there will be n choose r things, like r things. Case 2, x is not a subset. And in that case, we still need r plus 1 elements. X is not one of them, so it's going to come from these remaining elements. So then it's r plus 1 elements. And so by the rule of sum, n choose r plus 1 subsets. Okay, and so this is the other way. That's the left-hand side of the proof. Okay, so just as a concluding statement, therefore, choose r plus 1. That's a very quick way of doing it using counting. Okay, I have a couple minutes. It's time for me to review the binomial theorem real quick, and that will end things for this lecture, and we'll clean up the other stuff. Okay, so everybody has seen the binomial theorem from grade school last year, and we are taking an expansion of x plus y to the n will give us coefficients of polynomials that are of this type. Everything is going to have a degree of a total of n. Powers of x and y total. Now, what is the binomial expansion? Binomial theorem say you're using the binomial coefficients, and that's probably the thing that we use Pascal's triangle for the most. 1, 3, 3, 1 is the expansion. Right? So if we do this, the coefficient should be 1, 3, 3, 1. Okay? So writing this thing out longhand. So subbing this in, x to the I, y to the 3 minus I. Okay, I'll write this thing out longhand. Sorry, I'm going to go over here. X to the 0, y to the 3 minus 0. 3, choose 1, next to the 1, 3, this one. So all of them appear to be tag. Okay, but simplifying this thing down, right, next to the 0 goes away, 1 goes 0, we end up getting this very familiar thing that we're trying to increasing degree. Just keep going with this. So this is something that we're familiar with from grade school shorthand using Pascal expansion. Typically, we're asked questions like this, right? What's the coefficient of x to the 43 and x to the 50? You would never expand this thing and write out 50 terms, 51 terms, right? It's crazy. Okay? You can instead plug out the 1 of degree 43 from the line. Okay? So this is the shortcut that you can use. So solution. Doesn't really matter what's there, because 1 to the anything is proof. Okay, so we're looking for the term where I is equal to 43. Sub that in. We can choose one. Okay, so we examine the term. Don't need to expand out 51 terms to get the answer here. Just plug it. Okay, I'm a couple minutes over, but we'll get those back to you eventually. Thank you once again. We'll see you.